Okay, so we're going to take what we now know and put it to the test. So we've got a data set of 54 cholesterol level in 54 patients. So we're going to use all of our tricks to calculate mean, standard deviation, verify the bell curve, that sort of thing. And then we'll get down and talk about these other questions here. So let's take out our calculator and we're going to go to stat edit and then let's just type in all these numbers here. So hopefully at this point we're feeling pretty good about typing the numbers in and working with it to get whatever calculations we need. So let me pause it, let me type it in, let you type it in, and then we'll jump in when we find out the mean and standard deviation. Okay, so we're gonna go. We need the mean and standard deviation, and I think one of our stats will get that job done. So we're gonna go over to Calc to one of our stats, and then I want to tell it to go to list 2. I'm sorry, list 1. Go to list 1 to calculate that. Okay, so our mean is 57.4, and we have two numbers to pick from as far as standard deviations. There is a right choice. What we have to ask ourselves is, are we looking at a sample or a population? And it gives us the population of patients. So it actually tells us we're dealing with the population. So we're going to stick with the population standard deviation, which is the 11.6, 11.7. So let me write this down here. We had a mean of 57.4, and we had a standard deviation of 11.7. Okay, so then we want to create a histogram and verify whether or not the data is bell-shaped. So we go up to stat plot, just make sure that our stat plot is turned on, and if it's not, just highlight it and make sure that the histogram icon is picked. And then we go to zoom, and then we want zoom 9, so zoom stat, and we get a nice pretty picture, and it's fairly symmetrical. You'll find in statistics we don't really have a perfectly symmetrical graph, but it's enough symmetrical that we can treat it as such and answer these other questions. So you can, if you're wanting to copy and paste this into your notes, remember you can hit trace, and trace will tell you what the numbers on the bottom are, and will also let you scroll around. Speaking of which, let's confirm that we have the right numbers. It looks like we have a max of 92 and a min of 35. So let me go back to here. If I go 92 minus 35, I have a range of 57. So if I want to see about 10 rectangles, which is typically what we'd like to see, again, not set in stone, I should have the interval width should be about 5.7. So if I go back to window, let's see, I should be able to change that. Right now they have it at 7.1, so I can switch that to 5.7, and then that will give me a little bit nicer graph that I can see, but again, not required. And when we do that, when we switch it to, we get 10 rectangles, it does have a little bit more of a symmetrical look. The other one seemed to be a little skewed, but mostly it was symmetrical. Anyway, so you can hit trace, and then it will give you the numbers that go in the for the rectangles as far as how many observations there are and what the bounds of the bottom part of the rectangle are. Okay, so we want to determine the percentage of all patients who are within 3 standard deviations of the mean according to the empirical rule. Well, according to the empirical rule, within 3 standard deviations, that's 99.7%. So that's just a theory question. Let's see, and then let's actually come back up here. Well, yeah, let's think about when we set these numbers up. If I am 57.4 is the middle, if I go 11.7 above it, so 57.4 plus 11.7. Let me try that again. 7.4 plus 11.7. I get 66.8. Sorry, 68.8. All right, and if we keep adding, I'm going somewhere with this. So if I add 11.4, I get 80.2. So now I'm 2 standard deviations above. And if I add another 11.4, I'm at 99 or 91.6. All right, so let's go. I'm going to highlight this and so it stands out. All right, so let's go the other direction. If I go 57.4 minus the 11.4, I get 46. So we'll go one more, two more below. We'll keep going. So minus 11.4, I get 34.6. And we'll do it again. Minus 11.4, and I get 23.2. Okay, so let's go back to this question here. What percent is between 34 and 69.1? Well, we're looking at this region here, where the 46 and the 68 happen to be between 1 standard deviation, and we add in that 34. And again, this is an estimate. Eventually we will learn how to get exactly the percent, but these numbers are nice enough that we could sort of estimate this. So we're looking at these two being 1 standard deviation and that being the second standard deviation away. So I go back up to my chart. I have 34 and 34, 1 standard deviation away, and then I have another 13.5 in that direction. So if I add up the 34 plus the 34 plus the 13.5, about 81% should fall within those two numbers, 81.5%. And again, this is an estimate. We're going to get more detail later on. Let's see. Determine all patients that have the serum between this and this. Okay, so this last question is asking determine the actual percent of students that have a serum between 34 and 69.1. So if we come up here and we count how many of these actually show up within that range. Now I'm going to use a little calculator cheat on this, not a cheat sheet, but let me go to stat. Let me sort the list. Sort ascending for list 1. And when I go back into my list, let's put it in order. And I want to know between 34 and 69.1. So let me count the ones that are not 34. So that would be, oh, that's nice. Okay, so none there. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 of them above 69. So of the 54 observations, there are 45 of them that fit within that range. So if I go back here, 45 divided by 54, there are 83%. So our estimate was 81.5% based on the empirical rule, And in actuality, for this particular data set, there's 83%. So that's not bad. That's a fairly symmetrical data set, pretty close to the expected there. So that's what that last part's asking. Okay, so the last part that I want to talk about is a Russian mathematician named Chebysevsky's inequality. He came up with sort of a different way to look at the bell curve. What if we don't know if it's symmetrical? What if it's skewed, or all these other generalities that we can take? And so he noted that if we look at the observations, that we would expect this formula, this 1 minus 1 over k squared percent to lie within a certain standard deviation of it. So this is really just a formula question, sort of a strange math question that shows up here. But so determine the percent that lies within 3 standard deviations of the mean. I would replace the 3 with the k with 3. So let me just type that in here. So parentheses 1 minus 1 over 3. Sorry, I want that squared. Times 100%. So I would type that in a calculator and calculate that. Okay, so typing that in a calculator, I get 0.889 times the 100%. So that means I would expect 88.9% of the data to fall within 3 standard deviations according to this formula. Okay, so this last question, they're saying determine the actual percent that fit between 34 and 80.8. Now remember, we have that sorted data, so I can just go back to our list and I can look between those two values. So 34, we don't have anything on that end, but above 80.8, so we have 1, 2. Okay, so we only have 2 that are above. Everything else would be between. So I want 52 divided by 54, which as a percent is about 0.96. So we're looking at 96% of the data is actually between those two values. Anyway, so it's just this theorem is just a different way to calculate percents. We'll stick with the empirical rule for the most part, but it's nice to know there's other options out there. So.